Sand moves in different ways along our coastlines. It moves back and forth, and that is typically going to be thought of as being seasonal. So this is split into the summer berms and the winter berms. In the summertime, sediment is going to move onto the beach, and you'll have that lump that is the summer berm. Then in the winter, the storms are going to grab at that sand, the high energy waves, and pull it back off the beach. And then you'll have deposition out here in sandbars out in the ocean. So removing it from the shoreline, eroding it back out into the ocean. The other way that sand moves is along the beach. This is called longshore transport. So it's transporting the sand within the surf zone down the beach in the direction that the wind is blowing. And the reason that is the case is the direction the waves hit the beach is dictated by the direction the wind is blowing. So in this diagram, those wave rays, those arrows coming in, imagine that's the wind. And so the waves are perpendicular to those wave rays. The waves come into the beach and the water is going to zigzag. It goes up the beach and then swashes back down the beach, up the beach and swashes back down the beach. So it goes up the beach at an angle, but then down the beach because of gravity, kind of straight down, perpendicular to the shoreline or the direction that water would flow down the beach. Okay, so let's look at this little animation here. Let me pull up my screen. There we go. Okay, oops, I already watched it a little bit. Let me go back to the beginning. Okay, so there's no sound. Aerial view of a coastal beach. Here's a sand particle. And the wave is going to come in and move that sand particle to the shoreline. Right, there it is. Washed it up onto the shore, and then as the wave, and this perpendicular to the beach is going to go straight back down into the water and up the shoreline again. And so it's kind of a zigzagging motion for that piece of sediment. There it is, a zigzag motion. That's longshore drift. Okay, there's another video I want you to watch coming up.
Do you like going to the beach on a hot summer day? Yeah, me too. There's nothing like the sound of waves lapping at the shore, or the feeling of warm sand between your toes. Today we're going to have a closer look at that sand and those waves. This video is about the transport of sand along a shoreline by the waves. The process is called longshore drift. Imagine you could shrink yourself down to the size of a grain of sand. This is what you would see. Sand is an incredibly strange and intricate substance, as you will know if you've ever looked at it under a microscope. Now that you're just a millimeter or two tall, your experience of the world is going to change dramatically. For one thing, you're now light enough to be blown around by the wind, and there's nothing you can do to stop it. In a beach environment, sand can be transported or eroded by many different forces. There's the wind, streams flowing from the land, animals getting sand stuck in various places. Oh, and the waves, of course. Ocean waves are the most important force of erosion in pretty much every coastal landscape. A sandy beach is no exception. If you're a grain of sand chilling out near the shoreline, you are completely at the mercy of incoming waves. It doesn't even take a particularly big wave to pick you up and fling you higher up on the beach. As the wave retreats, you may get pulled back down the beach to await the next wave. This is going on all the time. Sand is being shoved back and forth along the face of the beach all the time. Or is it? Take a closer look around. Are you in exactly the same spot you were before that wave caught you? Probably not. In fact, if you follow a sand grain for a few hours on almost any beach in the world, you see an interesting pattern. It gets moved sideways along the shoreline in a kind of sawtooth pattern. Every grain of sand zigzags along the beach. Why does this happen? To answer that question, we need to look further out to sea, to where the waves are created. Waves on the surface of the ocean are a response to the prevailing wind. In different parts of the world, prevailing winds blow in different directions, and they may change direction depending on the weather. For this explanation, let's just say the prevailing wind always blows from the northwest. The waves that are generated by this wind travel in the same direction, so in this case they will strike the beach from the northwest. They push sand grains up the beach in that same direction. This movement is called swash. Then, as the waves retreat and flow back down the beach, the sand grains follow the influence of gravity. They move back down the beach at right angles to the shoreline, following the natural slope that exists there. This movement is known as backwash. Repeated swash and backwash movements cause that zigzag pattern we saw earlier. Overall, the sand is moved sideways, parallel to the shoreline. This is longshore drift in action. Longshore drift not only transports sand across a beach, it uses that sand to build some stunning landforms. For instance, this is a satellite image showing Provincetown Spit in Massachusetts, USA. And this is Farewell Spit in New Zealand. A spit is not as gross as it sounds. It's a long bar of sand that extends out from the land into the ocean. This one is an impressive 26 kilometers long, with another 6 kilometers stretching under the water. It is all made up of sand that was transported by longshore drift. Now you should be able to draw a diagram like this to explain how longshore drift works. You might also like to learn more about landforms that are formed by longshore drift. I will put some useful links in the description if you'd like to know more about this process. That's all for this video. Thank you for watching. I hope you found it interesting.
Okay, how do we get back to where we want to be? Here we are. All right, longshore drift. So it's important to think of beaches as this really, really dynamic environment, that it's a strip, a pile of sand. And every wave, every storm, all the currents are manipulating that sand over time. So we can really think of beaches as being kind of geologically temporary, or at least think of their location as temporary. So with sea level rise and fall, if sea level is rising, beaches move inland. If sea level is dropping, then the beach is going to move out towards the sea. So that's transgression and regression. Transgression would be up the beach, and regression would be sea level dropping and down the beach. So humans, we go out to the coastlines. They're wonderful places to be, right? And we build a house, or we put in a hotel, or an amusement park, or whatever, a road, whatever it is. And we add the infrastructure that goes along with that, roads, sewer systems, water systems, electricity. We put that out there by the beach, and then storms come and sea levels rising, the beach erodes. So we try then to stabilize beaches. And we're going to talk about some of these stabilizing attempts that occur along our coastlines. We call them hard or engineered structures, and they disrupt the longshore transport. All right, here's the list. So common stabilization projects include things like groins. Groins are built perpendicular to the beach, and they attempt to trap sand. Seawalls are built parallel to the beach, and they attempt to protect infrastructure on the landward side of the seawall. Beach nourishment is not really an engineered structure. It is pumping sand from one place and squirting it up onto the beach. There are harbors and river mouths and inlets that we use for navigation. And so to protect those, oftentimes people will build what's called jetties. And that would be almost like two groins out on either side of a navigational channel to hold that inlet into place. And then there's dredging, lots and lots of dredging. Intercoastal waterway gets dredged all the time, and canals get dredged because they fill up with sediment over time. So here's a jetty on either side of this, the river coming in. There are hard structures, so here and here. So what this has done, look at it a little bit harder. and see that on the right side, we'll just call it right and left, there's a buildup of sediment. And on the left side, there's way less sediment. So if you had to guess which way the longshore transport is, you might would guess that it is from this direction where my face is over to the left. And so sediment piles up behind this jetty here, and now we've starved this down beach section, and that is experiencing erosion. Okay, so here is kind of over time what has happened. So we'll go back. Here is a brand new jetty put out there into the ocean to protect that navigational channel, and then boom, over time they've lost like so much beach over this top half during a storm. Here are groins. So the groins, what happens with groins is when you put one out, it's usually what they call the slippery slope, and more groins get put out, and so that you have a field of groins versus just one. And these are acting to trap sand behind them. This is what it looks like. So in practice, so here's the groins, are these hard structures, usually like piles of rock, chunks of concrete, and the wave fronts are coming in. The longshore drift is to the right, and D stands for deposition. That's where there's deposition, and then behind them is going to be erosion. Okay, so you have to put more than one, because there's going to, down the beach, there's always going to be erosion, so you've got to trap more sand. Here is a fan along this point here. There's tons of groins here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this would be the direction that the sand is coming from. Up here, it's coming around this corner with a current, and the groins are trapping it behind each one. This big one here, trapping lots of sediment, and looks like these were probably built early on, and then these later were built as they started to experience erosion in the shore face here. All right, this is just showing again that you're gonna be moving sediment down the beach. So I think of this in terms of me or my kids. We spend a lot of time at the beach, and we go out in the water with our raft, right? You get in, and like 15 minutes later, your mom's yelling at you, "Y'all get back up out of the water and walk down the beach, get back in front of me." That's what my mom sounded like, and maybe I do too. But that current that's taking you and your raft down the beach is the same process that's carrying sediment down the beach. Okay, so here's waves coming into the beach. These are almost like parallel to the beach, right? More waves coming into the beach. This erosion has caused these houses to be like on the shore face. That's not good. What happens then is over time, right, pieces of these houses are going to fall into the water. Maybe there's a sewer system that could be breached. So it's really good to go ahead and, I don't know, get out of the way, move the house, because there's going to be lots of trash on the beach. And if you're a person that doesn't own that house and you want to hang out on the beach, you're like hanging out in their front yard, just move the house out of the way. Easier said than done, right? So I'm going to turn my face off. These are sea walls. What happens with that is if you build on the land, obviously the land side, and there's lots of infrastructure and there starts to be erosion, you get nervous, you're going to put up a wall. And these, we call this the New Jerseyification. Ugh, unfortunate term. But putting up a seawall, okay, so here's the beach. It's pretty wide. Put up a seawall, the initial shore profile is going to stay the same, but over time the beach is going to be lost. The waves actually hit that wall and bounce off and generate more energy as the waves go back out into the sea. That reflection, right? So over here, that's not like a nice place you want to hang out on the beach, nor here, this messy graffiti covered wall. All right, another engineered structure is a breakwater. Breakwaters are kind of cool. They are put at the shoreline to dissipate energy. They can protect a harbor, a campground, maybe protect a moored boats that are out in the water, but they do over time change the shoreline. So notice on here the waves maybe were coming in and they get around these breakwaters, but as the waves go in, there's going to be like a quiet zone in the middle where there's deposition, and then it's going to come whip it around that breakwater and cause some erosion. So there'll be a weird erosion and deposition patterns that maybe weren't anticipated when the breakwaters were built. In the United States, let's see, the yellow shorelines are relatively stable. The orange ones are moderately eroding, and then yellow are hot spots of erosion. If we go in and look at North Carolina, I'm mostly familiar with like the Brunswick County islands that hover around the North Carolina, South Carolina border, and there's lots of erosion in that area. Also out on the Outer Banks, there's lots of erosion. And here at the Georgia coast, it's really sad. There is some erosion, but that's pretty stable too. The severe erosion are these pink areas. So all along the coast of Louisiana, the northern part of the Outer Banks, New Jersey, Connecticut, Rhode Island, Massachusetts, lots of erosion. So moderate erosion, relatively stable, and severely eroding areas of the North Carolina, United States coastline. All right, beach nourishment. This is controversial. Turn my face back on. Hi. Controversial projects. You go to what they call the borrow site and you pump sand onto a beach. This beach here has some groins. The beach is eroding. They needed to build it back up. So it's artificially placing sand on beaches. You're adding to the beach budget. The beach sand budget is like balancing addition and subtraction of sand, right? The longshore currents should just keep bringing sand along, but sometimes that's screwed up. So beach nourishment does protect coastal property, but it's really expensive and it may not last very long. In the 50s, they spent $62 million on a beach for Miami, and it's still there. In the 80s, they keep pumping money into the shorelines in New Jersey, millions of dollars, and then it just erodes away in a couple of years. So it does make a nice beach, nicer than a seawall, but it's expensive and it can erode over time. What you have to be sure of is, excuse me, the sand quality. You don't want, I hear a lot of complaints sometimes with beaches that there was a nice smooth sand beach and the dredged sediment will have like chunks of seashells in it, and people don't like that. Okay, rip currents. This occurs, I think we already talked about this with waves or tides. When usually it's wind is pushing water up onto the beach, it'll kind of stack up onto the beach, and then gravity will rush all that water back off the beach. So coming here from sea, it's going to come rushing back off the beach. Erosion. These waves coming into the beach are going to be focusing in on this elevated headland, because from the elevated headland out into the ocean there's a ridge. They're showing that ridge here, and that waves are going to bend. And so when they bend, these wave rays, the yellow lines, show that the energy is going to come into that headland. And then here where the energy is not focusing, you would have deposition in a bay. So at the elevated headland there's erosion, and in this back bay there would be deposition. Here's a headland that has lots of wave energy and erosion, and then quieter waves over here in the bay where there's deposition. There's the bay. The wave rays come in, and they are the waves are going to be bending, and so the energy is dissipated. There is a bay with less energy in it, and so just kind of happy little waves and deposition of sediment. Another bay. Wouldn't it be nice to be there right now?